Hello, in this video we will talk about significant figures. And before anything, let me show you this little drawing. Let's look at the difference between accuracy and precision. Remember, we discussed the need for experimentation in science and how, well, we need instruments to not necessarily rely on our senses. So any instrument, when you make a measurement, usually you don't take the measurement only once. You want to repeat the measurement, you want to repeat the experiment, and when you do that, you can have results that are accurate and precise, or not accurate nor precise, or a combination of both. So accuracy is more related to how close you are from the real value, right? Look at this. This is very precise, but it's not accurate at all. And that helps us understand precision. Precision is when your instrument gives you measurements that repeatable measurements, right? Here, we are accurate, we're close to the center, we are all over the place. So basically you want accuracy and precision, but it's, okay, that's the ideal. Now, no matter what instrument you have, it's going to have limitations in terms of accuracy and precision, right? There are inherent problems when you have a device, a measuring device. Let's start with something simple like a ruler. If we look at these two rulers, we're measuring the same candy, but ruler B is more precise. With the first one, you will say, well, the candy measures between 4 and 5, but you really don't know more. All you can say is that it is between 4 and 5 centimeters. Let me make it in my... With ruler A, you can say it's between 4 and 5 centimeters. But with ruler B, you can say, oh, well, actually it is 4.3 centimeters. Now, the thing is, here we have more subdivisions in ruler B, right? It's more precise. But what if the candy, let me draw a candy here, another piece of candy, and this one falls somewhere in between two lines here. Well, it's difficult to draw, but it's between, as you can see, is between 4.56 and 4.7. You see, now we cannot tell anymore. There is some uncertainty. There is some uncertainty. We are in between 4.6 and 4.7. So we use significant figures to express the uncertainty in our measurement. You see, we are between 4.6, 4.7, no less than 4.6, no more than 4.7. This is already one valid way, centimeters, of course, to express our measurement. Another one will be to say we have 4.65 centimeters plus minus 0.05 centimeters. You see, if you write it like this, you're writing the same thing as that, because 4.65 minus 0.05 gives you 4.60, and then 4.65 plus 0.05 gives you 4.70, which is exactly what we know as a fact. So one piece of information we extract from this is that the uncertainty of our measuring device is plus minus 0.05 centimeters, which means half plus minus have the smallest subdivision. In the case of this ruler, of course, is 1 millimeter, which means 0.1 centimeter. So 0.1 centimeters over 2 is 0.05. And this will be one way to express our measurement in what we call absolute uncertainty. Notice that if this is in centimeters, this is also in centimeters. So if we need significant figures to talk about uncertainty, let's talk about significant figures first. If we see these two numbers, 0.03 and 0.0075, well, when you have zeros to the left, they don't count. In this case, we will have one significant figure. In this case, we have two significant figures. That's 0 to the left. 0 to the left. Oops, 0 to the left. Now, 0 to the, my God, 0 to the right. If you have, let's say, 1500 grams. Okay, so here there is room for interpretation. When you see something like this, some people might think that the two zeros here are significant because that means this, that you have a decimal point there. But other people might think that they are not significant. So some people see this and they read 4 significant figures. Some people read only 2 significant figures. To eliminate this problem, the best thing you can do is use scientific notation. So, because if I write this like 1.5 times 10 to the 3 grams, then I have 2 significant figures. But if you write 1.500 times 10 to the 3 grams, then you took the time to write these 2 zeros. So that means you know for sure that this is a 0 and this is a 0 and not any other number. So it is significant. So in this case, you have 4 significant figures. The same rule applies even for zeros to the left, or when you have where you have ambiguity. So if you see 2.3 times 10 to the minus 4, then you say it's 2 significant figures. But if you see 2.30 times 10 to the minus 4, well, now again, somebody took the time and effort to make sure this is a 0 in their measurement. So this is 3 significant figures. Now, when you have to perform mathematical operations with respecting the significant figures, if you multiply, there's a multiplication or a division, the number of significant figures in the final answer is the same as the number of significant figures in the quantity having the smallest number of significant figures. Right? So we keep the smallest number of sig figs. Right? If you multiply 32.3 times 41, this one has 3, this one has 2, so the answer will be, in the calculator will give you all this, 1,324.3. That's what the calculator is going to tell you. But 1, 2, 3, 4, 5 significant figures, which makes no sense. So the actual number you need to write will be, well, you should actually only keep 2. So is 1.3 times 10 to the 1, 2, 3. This is the number you will write. In scientific notation, right? Why not? So you only have 2 significant figures, which makes sense because we keep the smallest amount of significant figures in a multiplication or in a division. What about if you add or subtract numbers? Well, the rule there, oh, something moved here. The rule there is that when you add or subtract, the number of decimal places in the result should equal the smallest number of decimal places of any term in the sum or different. What it all means is that we keep the least or smallest number of decimals. Let me give you an example. If we have the same third, well, let's do something a little bit more interesting. Let's say 32.3 plus 6.189. Okay, so if we do this again, this will give you 38.489. But again, we now have to take a look at the number of decimals. This one has 1. This one has 3. So we have to keep only 1. So the right answer will be 38.4. But, well, I didn't tell you this before, and I'm sorry. We have to round. So, of course, if we round to the closest, in this case, we have 48. 48 is closer to 40, is closer to 50 than to 40. So we will just put, oh my God, let me find the eraser. So we will round up to 38.5, right? And then you do the same with subtractions. So again, for the addition subtraction, what matters is the number of decimals, not the number of significant figures. We chose 38.5 not because this has 3 significant figures, it's because it has 1 decimal. And notice these 2 examples in the book. They're interesting. I'm going to use the other 1.0001 plus 0.00003. which gives us 1.0004. 1, 2, 3, 4, 1, 2, 3, 4. So there you go. We keep the 4 decimals. And notice that this number only has 1 significant figure, and yet the result has 5 significant figures. On the other end, if we have 1.002 minus 0.998, the result is going to be 0.004. So we go from 4 significant figures, or 3, to only 1, because what mattered was the least amount of decimal places. To avoid issues with multiple steps, one good technique is to use symbols as long as you can. Solve your problems using symbols as long as you can, and then at the very end, just perform the operations. Another thing in long calculations, you can delay the rounding of numbers until you have the final results in order to avoid error accumulation. So delay rounding, okay, until the last. In the next video, we will talk more about how to deal with the uncertainty propagation